Hello, this lecture will introduce the topics that we'll be covering in CSCE 611. This course will cover the techniques or the methodologies in which large-scale digital systems are designed. In other words, this is a course about hardware design as opposed to software design, which is the focus of most of the other courses you've taken. Why are we teaching a course on hardware design? Because there's plenty of off-the-shelf computer processors available that can be purchased, and they all have the same capabilities. CPU is a CPU. Or do they? Take, for example, the Summit supercomputer in Tennessee. It can perform 200 quadrillion operations per second, and it uses 10 megawatts of power. Surprisingly, or you may be surprised, that any software that can run on the Summit supercomputer can be recompiled and run on the Arduino chip, the ATmega 328P. But the Arduino chip can only perform 200,000 operations per second, but it uses only 20 milliwatts of power. So, despite being able to run the same software, Summit is 1 trillion times faster than the ATmega 328P. But even less obvious is that Summit is actually more energy efficient than the ATmega chip. You heard me right. Now, how can this be? We can measure energy efficiency as the power in watts, also joules per second, divided by throughput, or in this case, operations per second, or more specifically, floating point operations per second, or flops. The time units cancel out, giving us joules per operation, or joules per flop. Summit, when delivering 200 petaflops per second at 10 megawatts, is only expending 50 picojoules per operation. The M328P, on the other hand, when delivering 200 kiloflops per second at 10 milliwatts, is expending 1 microjoule per operation. Thus, Summit is 20,000 times more energy efficient than the 328P. Now, these are abstract concepts, though, but they translate into more tangible capabilities. For example, prior to 2014, there were no commercially available cars that had self-driving capability. This wasn't necessarily because the sensors that didn't exist, or the lane detection algorithms didn't exist. It was because of the introduction of high-performance embedded processors that were up to the task of processing multiple simultaneous video feeds and other sensor feeds simultaneously. For the same reason, prior to 2015, there were no cell phones that could record 4K video. Prior to 2017, there were no phones that could perform Face ID. Animojis didn't exist prior to 2017, and prior to 2018, there was no computational photography, which simulates the use of more expensive cameras and lenses on an inexpensive camera. But these advances weren't achieved by simply installing faster computer processors. They were achieved by designing entirely new, specialized computer processors designed specifically for each of those capabilities. Now, you might be familiar with Moore's law, which states that transistor density, and thus the number of transistors that you can fit on a fixed surface area, doubles every 18 months to 2 years. From the mid-1980s to about 2010, Moore's law translated directly into performance gains for general-purpose CPUs. In other words, a doubling of the number of transistors meant that you got a doubling of CPU performance. Sometimes these dramatic performance boosts cause problems with software. For example, you would buy a new computer and it would cause your computer games to run too fast for you to play them. For this reason, computers sold from the late 1980s to the early 2000s all came equipped with a button labeled turbo on the front of the computer case, right next to the power and reset buttons. When you turned on the when you turn on the turbo button, the computer would just run at its natural native speed. And if you turned it off, it would cripple the performance, which was designed to allow some software to continue to run as you expected it to run and as it ran on the previous generation of computer. Starting in 2010, however, Moore's law continued, but general purpose CPUs stopped getting faster at the same rate. So this table shows the peak performance indicators of the previous 10 years of Intel desktop CPUs. Now these are peak performance indicators. These don't indicate the performance you're actually going to get, but this is the upper bound in the performance you could get, the physical performance limitations of these chips. The tech column shows the transistor width, which scales from 32 nanometers down to 14 nanometers. Now that doesn't seem like a lot, except you got to keep in mind that the transistors are two-dimensional structures. So as the width scales down, the length scales down at the same rate. So the transistor area scales according to a square of the width. So a 32 nanometer transistor is 5.2 times larger than a 14 nanometer transistor. The rate of improvement over 10 years is for any of these metrics is calculated by taking the 10th root of the ratio of improvement. So as such, a 5.2 times improvement in transistor density, and the number of transistors you can fit, because you've reduced the size of the transistors by a factor of 5.2, translates into a 17% per year improvement. At a given improvement rate, you can calculate how long it would take to double a particular metric, which is basically the log of 2 divided by the log of the improvement rate. So this gives a doubling rate in the number of transistors of 4.4 years. Now that's longer than the ideal Moore's law rate of 18 months to 2 years. So obviously Moore's law is slowing down in the last 10 years. However, if you use the same calculation, performance indicators such as the clock rate, instructions that can be executed per cycle, the number of processor cores per CPU, the maximum memory bandwidth, and the size of the last level cache have a longer doubling rate over this period. The good news is that floating point performance is keeping pace with Moore's law. Floating point is used whenever an application or software requires arithmetic that is based on real numbers for fractional numbers, basically. The bad news is that GPUs have always had a 10x advantage over CPUs in doing floating point. So anyone who requires floating point is going to use a GPU. So essentially meaning that no one's using floating point on CPU, at least in cases where performance is a factor. Intel understands this, and you can see their strategy for dealing with this problem. If you look at die photographs or chip photographs of the previous 10 years of their Intel processors, the processor from 2010 allocated or set aside 72% of the chip area for the CPUs, and the remaining 28% to specialized logic, specialized hardware for memory and I/O performance. The next processor added specialized hardware for graphics and video, which shrunk the CPU part, the general purpose CPU part of the processor, to 47% of the chip. And this trend continued until now the processor area is less than 20% of the chip in newer chips. The other 80% is all special purpose hardware for accelerating specific things, for speeding up specific calculations. Chips that power embedded systems, such as Apple's iPhone, iPad processor, have always allocated most of the chip area to specialized hardware designed for specific capabilities. Outside of embedded systems like phones, specialized hardware is becoming increasingly prevalent in other areas, even in the data center, like in server rooms. Nearly all warehouse scale computers are augmented with specialized processors, such as GPUs, tensor processor units, and other types of processors designed for machine learning and data analytics. Development of specialized hardware is basically required whenever you want to deliver a new capability. So whenever Apple comes out with a new cool capability, you can bet that there's been hardware designed specifically for that on the chip. It's also happening behind the scenes, as I mentioned, in the cloud and on the desktop, in desktop processors that are trying to keep up with increasing demands for higher resolution video and higher performing graphics rendering. Now, specialized processors are faster than general CPUs. Why? The first has to do with the memory wall, in which the external memory often becomes a performance bottleneck, limits the performance for many types of applications that require high performance. Specialized hardware, specialized processors overcome this by customizing the structure of their internal memories to minimize the use of external memories. The second reason why you need special hardware to deliver higher performance has to do with the power wall, which places a limit on the thermal dissipation of any chip. Basically, you can only dissipate 2 watts per square millimeter. Any more than that, and it's not feasible to remove that heat. Specialized processors are able to perform more work within this limitation by being able to reduce overheads that are required by general purpose processors. So, they strip out everything that they don't need and everything that doesn't directly contribute to the task at hand. So that being said, in this class, we'll be designing a general purpose processor, ironically, but we're doing that to demonstrate the tools and the methodologies needed to design any large-scale digital design. And I will begin describing these methodologies in the next video. Thank you.